Yeah. This is the second week, and then we will discuss the new material. First of all, I will give you the notation for our lecture. This represents the empty set, and then the absolute value of set A means the cardinality of A, that is the number of elements in A. And then this notation represent the function from the domain A and its codomain is B. And then this notation means X is a member of a set A. And then this notation means X is not a member of A. And then we use this notation for the subset. That means all members of A are contained in B. Okay, we will use this notation for our lecture. Then we start with the first topic today. It is the sample space. A sample space actually a set that contains all possible outcomes of an experiment. So if we do an experiment, such as we toss a fair coin, not to be fair, at least we toss a coin that have a coin that has two faces, that is the head and the tail. So the all possible outcomes are H and T. And then after that, we put H and T into a set named S. So the sample space is S, which contains H and T. This is because we only have two faces for our coin. And then for the experiment of rolling a six-sided die, we can note that all of the outcomes are the 6 point. That is the first one only contain a point, and then 2 points, 3 points, and then until 6 points. So in this case, in this experiment, our sample space is the set S, which contains 6 elements. They are 1, 2 until 6. These are two basic experiment, and we are familiar with them. Okay. Do you have any question for our simple example? Yeah. Okay. Yeah. In conclusion, a sample space is a set that consists all possible outcomes. So we must list all possible outcomes of that experiment. Okay. Then we move to the next example. In this example, we deal with a die which has 8 sides. Okay. What is the sample space of this experiment? Okay. Who knows this sample space? Please open your mic.
Is it 1, 2, 3, 4, 5, 6, 7, 8, sir?
Yes, because we have 8-sided, so the sample space is 1, 2 until 8. Okay, thank you. And then for the next experiment consists of flipping 2 coins. What is the sample space of this experiment?
Head and tail, sir.
Only head and tail.
I think that it can also be tails and tails, head, and also tails and head.
Right. Because we have two coins that I illustrated with this. We have these two coins. Yeah, of course, our outcome are a pair. So we can write it by this notation, because if we only use if we write h, it means only a coin here. So we must write it in a pair, such as this h comma t, and then t comma h comma h, and thus is t comma t. And this all of outcomes of this experiment. Okay, thank you. And we must note that the first letter means it is from the first coin, and the second letter is from the second coin, and the order is important in this case. Okay, for the next experiment consists of rolling two-sided dice. What is the sample space? Six-sided dice. We roll two of them. Yeah, and if we refer previous example, for one die, we have the sample space is 1, 2 until 6. And then, of course, for the second die, the sample space is also 1, 2 until 6. What is the sample space of this experiment? Okay, let's imagine it if the first die shows 1, and the second die shows 2, and we can record this outcome with 1, 2, right? And then, of course, there are possible outcomes. Another possible outcome, such as 3, 2 or 2, 1, and so on. Yeah, and in this experiment, we have 36 outcomes, which is represented by this table. Yeah, there are 36 of outcomes. You can see in this table. So in the term of cardinality for this sample space, the cardinality is equal to 8. The cardinality of this set is equal 4, and yeah, the cardinality of this set is 36. And to simplify our notation, we can also write the sample space as the set of all pair A, B, where A and B are from 1, 2, until 6. Yeah, we can simplify this table with this set notation. Okay. Until now, is there any question from you? Okay, if there is no question, we continue our study. Next, yeah, this is an experiment that the rule is we toss the coin until we get a head. For the illustration, if the first toss we we directly have head, we can write the outcome with H here. And then if the first toss shows tail and the second toss shows head, we can write the outcome as TH. And if we continue it, if the first and two tosses shows T and the third is shows head, we can write the outcome as TTH. Yeah, and this is okay. This is the example of the outcome. Is there any outcomes different with these three? Is there any?
Maybe TTTH, three T's and one H.
TTH, yes. If the first, second, and the third toss shows up T, we can also have this outcome TTTS. And then is there any additional element, Owen? Can we
Yes.
produce this?
I think that it can go as long as possible.
As long as
It's
possible,
infinite,
right?
yeah.
Yeah, it is infinitely many. Yeah, as long as we get tail, we must toss again and toss again until we get a head. So for this sample space, we can write the sample space as HTH, TTH until infinite time. Yeah, right. Okay, thank you, Alan. And yeah, of course, the number is infinite for this sample space. Then we move to the next experiment that is consists of measuring the exact, that is the exact lifetime of a lamp. And then we will determine what is the sample space of this experiment. Note that we must write the exact time. Exact means we include the decimal. What is the sample space of this?
Is it infinite, sir?
Yes, it is infinite. And can you give us the definition of the set?
I think the set is all real numbers.
All real numbers, like this, right?
Yes.
Right. Okay. It's almost true, but let's think first. Is there any restriction for the lifetime? The real number. If we, yeah, that for example, this is the real line. This is 0, and then this is goes to infinity, and this is go to infinity. Is it possible for lifetime to be negative, right?
No. So maybe it's above 0 and above.
0 and above, right? Yeah. So for if this makes sense, that the lifetime is never be negative, right? So we must give a restriction for this set, that is x is greater than or equal 0. Okay, thank you, Said, for your answer. Yeah, and yeah, because we must find the exact value, so we use the set of real numbers, because yeah, we measure the exact value. Okay. I think that's all for our examples about the sample space. Any question from you? Okay, good. Let's move to the next the next concept. It is about the event. By the set theory, an event E is any subset of the sample space S. That is, E must fulfill this condition. That is, E subset of S. Yeah, it is similar with our previous example about population and sample. For example, if we have S the sample space, then an event is any subset of S. For example, the event is like this. E. Yeah, this is an example of the event in S. And of course, we can get another event such as this, and so on. Okay, one question from me. If I give you a set S, what is the trivial of in S? I mean, what is the event that is surely contained in S? Is there any one of it? An event that is obviously exists in S. Is there an events that is obviously exist in S? Or from our theory, for a set can become a subset of S if all of element in E is also it is. Yeah, please. Do you know what is the events that is clearly exist in S for every set?
Maybe date of birth, sir.
Date of birth?
In 1 month, I mean.
Yeah, thank you. But in this case, we discuss arbitrary set, not only for the number. It can be also a qualitative set. Oh, yeah. Oh, yeah. Okay. If there is no another response, yeah. I'm sorry if it is a little bit hard for you. For the point of view of set theory, if S is a non-empty set, then the empty set is always the subset of S, and S itself is also a subset of S. So if we have a sample space, we have at least two events on it. That is the empty event and also S itself. So yeah, for this for every set S, we obviously have these two events like that. Yeah, and yeah, I think you will get this knowledge from the mathematical logic. Yeah, maybe after midterm we discuss about the set theory. Okay, this is only for this only knowledge for you. Okay, and then that is continue from because I'm sorry. Because we will have many events, we collect them in a set denoted by 2 to the power of s. That is called the power set of s. And yeah, for the notation, it can be written as this set. That is the collection or the set of all E, such that E is a subset of S. And then from the set theory, we can see that if the cardinality of S is equal to n, then the power set of S has two to the power of n. This is the result from the set theory. Yeah, and this formula will be useful to us when we must list all of the members in we must list all of event in a set. And for example, if we have the sample space is S, which contains H and P, E1, a set that contains only H, is an example of event. That is the event a head appears on the flip of a coin. Then similar with E1, E2, this set is also the event of S, that is tail appears. And yeah, of course, from our previous discussion, the empty set and also S are also events on in S. Then for the next experiment, if we have the sample space is this is from the rolling of 6-sided die. We at least we have four events, that is empty set as itself, and then E3, that is 2, 4, 6, the event of even number, and E4, which contains 1, 3, 5, the event of numbers. Yeah, at least we from this example we get 4 of them. Yeah, and we also have another event that for example 1, 3, 6. Yeah, it is also an event in S. Okay. Okay. Then we said that the event E occurs when the outcome of an experiment lies in E. For the example, if we all die and the upper face shows 2, and from the previous example, 2 is an element of E3. So in this condition, we said E3 occurs. Yeah, E3 occurs because 2 is an element of E3. Yeah, and yeah, you can add more example of this definition by yourself. Okay. Okay. Next, because the events are also sets, we can operate them with some operations. Suppose that we have E and F, 2 events in S. For the first operation, we can find the complement of E, denoted by EZ, E to the power of Z, which consists of all outcomes in S that are not in E. As an illustration, if the sample space is this rectangle and the event E is the circle, then the complement of E is all elements of all outcomes in S that are not in E. That is this brown area. This is the complement of E. All outcomes in S, but not in E. For the second operation, that is the union of F, E, and F, denoted by this. It consists of all outcomes that are either in E or in F or in both of them. For example, if we have E and F like this, E union F will be all possible outcomes either in E or in F or in both of them. So this shows this green area shows the union of E and then for the last definition or the last operation, it is the intersection of E and F. And for the illustration, like this is E, this is F, and the intersection of E and F consists of all outcomes or all members that are both in F and E. So for the third picture, the intersection of E and F is this area. This is for E intersection F. Then, yeah, I hope this illustration can help you to understand these operations. Is there any question from you, please? Okay, great. After discuss about the operation of sets, we go to the interaction between two or more sets. For the first definition, that is two events E and F are said to be mutually exclusive or disjoint if its intersection is an empty set. For the illustration, we have this rectangle as the sample space, and two events are disjoint if they are not if they are separated. That is like this, E and F, and we can see that the intersection of E and F produce an empty set. So it is the illustration about two events E and F that are disjoint. Then to generalize it into n events E1, E2, and the En, we said that they are mutually exclusive if for every j and k from 1, 2 until n, and k and g are different, we get their intersection is empty. It is for every pair j and k. For an illustration, if we have n equal to 3, that is we we have three events, E1, E2, and E3. Like this illustration, you can check that E1 and E2 are separated, so their disjoint or their intersection is empty. And then the second observation, E1 and E3 are also disjoint. And for the final observation, E2 and E3 are disjoint. So this is the illustration that shows that this n element or these n events are mutually exclusive. Okay, and then for infinitely many events, that is a sequence of events E1, E2 until En, and so on, is said to be mutually exclusive if for K and G which are different, their intersection is on empty set. Yeah, this is the point 3 is the generalization from definition 2. Okay. Yeah, for finite case, we can see that these two events are mutually exclusive since their intersection is empty, right? And how about these two sets or two events, E1 and E2? Are they mutually exclusive? Please.
No,
No. What is the reason for this, Owen?
because they have both of them E1 and E2 have T and H, T comma H.
T comma H as an element that both in E1 and E2, right, Owen?
Yes.
TH and HT, I think yes.
Yes, that one
Right.
as well.
Yeah, we have two elements in their intersection. So yeah, they are not mutually exclusive. Right. Thank you, Owen. And let's discuss about the end events. In this case, we have this set S from 1 until n, and then we define E1 to be a set that contains only one element, that is 1. E2 contains 2 until En consists n. Now, for the illustration, 1, 2, 3 until n. This set that we group that into a circle like this. We group it into circle named E1, E2, E3 until En. And yeah, from this illustration, we can see that they are mutually exclusive. Could you receive the idea of this illustration? Yeah, it's like we give a catch for every number from E to until n. We give a catch. So yeah, it is helpful to give us the idea of this this concept of this fact that they are mutually exclusive. Yeah, we don't discuss the rigorous proof of this example because it needs more material from another subject. Okay, at least you can receive the idea of this this example, and then for the general case, if S is this set and we define EI as a set that contains I, we can see that the sequence of events are mutually exclusive. Yeah, actually, if you understand the first example, surely you can generalize it and understand the second example like that. Okay, yeah. I think this is the last slide for our material about events and sample space. Until now, is there any question from you? Okay. No? Okay, good. Let's move to the definition about the probability. We discussed the first definition, that is the classical one. In this definition, we assume that we have n equally likely possibilities. It means they have same probabilities to occur, and one of them must occur. After that, we have m of these possibilities as favorable to an event, or we set their success. Then from this definition, the probability of that event is given by m divided by n. As an illustration, if we have this box with 5 balls, 1, 2, 3 until 5, and we said that these balls are success, then the success event, or we said it is E. The cardinality of E is equal to 3, and our sample space contains 5 elements. So if we assume that these 5 balls are equally likely, then from the classical definition of probability, we get the probability of E is equal to 3/5. Yeah, this is the probability of E. We divide E by we divide 3 by 5, or the value of m divided by the value of n. Like this. Yeah, and if we discuss our previous experiment, that is we draw a balanced die. A balanced die means all outcomes are equally likely, and then we set A to be an event that an odd number occurs, and then we count the probability of A. Can anyone answer this question? What is the probability of the event A?
Half, sir.
A half?
Yes.
Yes, it is a half. Can you explain to us why we can get that number?
Because the sample is 1, 2, 3, 4, 5, 6, and the amount of odd number in the samples are 3. And
right?
because the whole samples are 6, you just divide 3 with 6, and you get half.
Yes. Great. Thank you. Yeah, because we assume that this is balanced die, so we can use classical definition. Then we divide the cardinality of A, that is 3, with the cardinality of S, that is 6. So the probability is a half. Okay, thank you. And yeah, let's move to the next example. We toss 2 fair coins, and then B be the event that at least one of these coins shows up tails, D, be the event that at least two of the coins shows up heads. And we must find the probability of B and the probability of D. Yeah, what is these values, PB and PD?
PB is 0.5, sir. Half
PB
is a half.
Teja, can you explain to us what is the elements of B?
It is heads and tails.
Oh, head.
Wait. No. Tails, sorry.
Could
Yes.
you?
Wait, heads and tails. Yes.
Before this, could you list all of the sample space? Yes. What is the sample space? Two coins.
Heads.
Head.
Tails. Tails.
Head. They like this, right?
Yes.
And then for B, at least one coin shows up tails. It's
I think I read the question wrong, sir. Yes. It'd be 0.25 because HT times EH.
Yeah.
Is that correct?
Yeah. So B consists of HT,
Or
TH, right?
TH and
TT. So the cardinality of B is 3, the cardinality of S is 4, right? And the PB is 3 divided by 4, right?
Yes, 0.75.
Okay, thank you, Teja, for your answer. And the last is D, event that consists of at least 2 heads. Yeah, I think it is obvious that the member is only HH. So the value of PD is 1/4. Okay, yeah. Thank you, Teja, for your answer. Yeah, I hope all of you can understand this example. And then in conclusion, for the classical definition of probability, we must analyze from the sample space and then count the cardinality, and then we consider the event. Then we write all of the elements of this event. After that, yeah, by the assumption of equally likely, we use classical definition. We divide the cardinality of the event with the cardinality of sample space. Yeah, and this definition is similar with our subject in high school, right? What is the different things in our lecture? Let's move to the next generalization of this definition. If we consider the previous example, there is a sample space that contains an infinite number, right? Infinitely element, right? That is the set of this. We flip coin until we get head. So of course it is the cardinality is not finite or it is infinite. So it is a problem. We have a problem here because if we use the classical definition, we must divide a number with infinity, and yeah, it's not make sense for this experiment. So the scientists develop a definition that generalize the classical definition. They called this definition by the axiomatic definition of probability. Let me see. In this case, we have S be the sample space and E is an event, and then we deal with a real valued function P from the set of all events in S to the set of real numbers R. We call this is a probability function if it satisfies the following statements. The number one is the value of PE is greater than or equal 0. Yeah, it is obvious because we don't speak about the negative value when we talk about the probability, right? So we use this statement in number one, and then for the next statement is the value of PS is equal to 1. Yeah, it makes sense because if we imagine the probability of all outcome in the sample space, yeah, of course it is 1, right? And then for the third statement is for any sequence E1, E2 until blah blah blah, which are mutually exclusive, then the probability of the union of all the events it's equal to E1 union E2 until blah blah blah. It is equal with the sum of all PE, PEI, PE1, PE2 until and so on. Yeah, we must, if this function want to be a probability function, it must follow these three statements. This statement is also called the axioms of the real the axiom of probability function. I mean, and the real number PE is called the probability of the event E. Is there any question from you for this axiomatic definition of probability? Please.
So the probability function is always be that, right? The 2 to the power of S.
Right. This function, this domain is always the event because we must assign, we want to assign all event in S to a real number P, like that side. Could you receive my explanation?
So the function will always be that for every sets or event.
Yeah, it is for general sample space and all event in S. Like we can because we write let S be the sample space. So yeah, it is for all sample space, for this sample space, or also for this sample space, and so many and so on. Okay. It is general for all sample space and for all experiment.
Okay, thank you, sir.
Yeah, and this axiomatic definition is a generalization. Actually, it is the generalization from the classical definition. It helps us to deal with the sample space that has infinite many elements. Okay, and then for our next communication, I write PA1, or PA means probability axiom, to denote this statement. I use this notation so we can recall them easily when we talk about another thing in the future. Okay, and then from the PA3, it looks like looks like generalized. We talk about a sequence. Let me see about the particular case of PA3. If we restrict it with the finite number, that is E1, E2 until En, from PA3, we can write this probability with this. If it is finite, we can list all of them like this. And then from PA3, this probability is equal to this summation, right? PE1 plus PE2 until PEn. We can do it by hand, count it by hand, right? Because we have only n elements or n values. And for the more particular, we will deal with only two events, A and B, which are mutually exclusive. Then we get that the probability of A union B is equal to PA plus PB, like this equation. Yeah, and yeah, these are the particular result of PA3. Yeah. Actually, we have another result, but we don't discuss it. Or we can discuss it more in detail in this meeting. You can refer to the video that I shared before, and using these three statements, we can get the next formula, that is the relation about PE and PE complement. That is PE is equal to 1 minus PE complement, or equivalently PE complement is equal to 1 minus PE. Yeah, it is they are equivalent. Yeah, and from this formula we can find the value of PE by using the value of PE complement. And then from this property, we can get the probability of empty event is equal to 0. And then for the value of probability A union B, we can see it is equal to PA plus PB minus PA intersection B. And we will get this result from these properties. That is, A union B is the union of these two sets, and you can analyze it by the Venn diagram. That every pair of these are mutually exclusive. So we will get these three equations. And then after that, you can use these three equations to produce this equation. And then for next result is if we have an event A that is a subset of B, then the value of PA is less than or equal to the value of PB. This is the last result of our discussion today. And to sum up them, I put these properties into a box that is 1, 2 until 5. This is the conclusion about the result of probability. And of course, you can use these formulas to count a probability. Yeah, for example, if from the previous example, if we have PB is equal to okay, let's back to our previous example. That is PB is equal to the 3/4 and PD is equal a quarter. Then B is D is HH. Then the probability of B union D is PB plus PD minus PB intersection D. And substitute the value of PB, that is this, and that is find the intersection. Yeah, because there are no elements in both B and D, we get that their intersection is an empty set. So we subtract these two numbers with 0, and then we get this is 1. So the probability of B union D is equal to 1. Yeah, it shows that our properties are very useful to answer our question. Then another usage of these properties is in this case of non-balanced die is which is loaded. Non-balanced means not all outcomes are equally likely. Yeah, I want to remind you that the term die in this lecture will affiliated by to the six-sided. So if I use the term die, this our assumption is it is six-sided. And then if we talk about the the die which not have six sides, we must write the amount of the side. So in this case, there are six sides, and then it is given that the probability of the number it shows up is e times k for a constant k. Then our task is to find the value of k. And yeah, of course, we will use all the statements PA1 until PA3, and then all of our previous properties. Yeah. To find the value of k, first of all, we must define an event. And yeah, and also of course the sample space. The sample space is this set, and then we must define. We will define the event AI. That is the event that number is shows up. So from this, we get AI is equal to E. And then by the previous example, we can see that these six events are mutually exclusive. And yeah, if we and then S is equal to the union of all of this. S is the union of all of this, and they are mutually exclusive. For the next step, which PA can be used for our problem? Is there any idea from you, please? They are mutually exclusive, and we get this equation. Which PA or properties can be used to solve this problem. We have so many properties and PA. Okay. One question. Can we use this property for solve for this equation? It is they are same, right? S equal to this union, so we can use this property to solve this question. Yeah, from from BA3 we can get PS is equal to the sum of PA1 until PA6. This is from PA3, and then because we know that the probability of number issues is E times K, we can get PA1. A1 consists of 1. It is equal to 1 times K, and then PA2 is equal to 2K, and so on until 6K. So if we add all of them, we get 21K. And from another PA, that is PA2, we have PS is equal to 1. So we have this equation, 20K is equal to 1. And then we choose that K is this fraction, 1/21. And the conclusion is the value of PAI is equal to I divided by 21. Yeah, this is the usage of all of some properties that we have before. Yeah, is there any question about the steps of this question, the step of the answer?
Sorry, sir. If we put for example, A8, so the answer will be 8/21. So is it correct or not?
If we have A8.
Yes. Sorry. A6. Sorry, A6.
A6. Yeah.
Yes. 6/21. Sorry.
Yeah. If we have A6, of course, from this result, the probability is like this.
Oh, okay.
Yeah, it is just an example, right? Yeah, thank you for your feedback. And yeah, you can change 6 by 5, 4, and so on. So yeah, if we see that the probability of each number are different, right? PA6 is this and PA5 is this. Yeah, in conclusion, the probability of number 6 shows up is greater than the probability of number 5 is shows up. Please, Kenda.
So basically the denominator is the sum of all sample of S, 1 until 6.
It is true if the given information is this, Kenda. Your statement is true because the probability of number E is E times K.
Oh, okay, so I got it. Thank you.
But if I change the information, not E times K, such as I write 2a times k, yeah, it is different, right? This brown definition is not only just of the sum of the sample, the outcomes, right? Can you get this difference, Kendra, and all of you?
On all of the numbers we times by 2.
Yeah, we times e with 2. Let's say I change the question, I change the information. The probability is not a times k, that is 2a times k. Yeah, you can write the denominator as the sum of these outcomes, right? They are different and depend on the information given in the question. Yeah, so you must consider the information from the question. Yeah, if we talk about the, oh yeah, I'm sorry, the next question is from the previous question. What is the probability that a number greater than 3 shows up? Yeah, from the previous slide we get PAI is equal to this, and then we must we will find the value of this event. Firstly, we define the event, and that is A is the event that a number greater than 3 shows up. And then to apply our properties, we must divide A into a smaller subset that are mutually exclusive, right? And then we use PA3. Now, for this goal, we define again AJ as the event that the number J shows up where J is equal to 4, 5, and 6. And then clearly, these sets are mutually exclusive, and A is the union of AI. I'm sorry, A is equal to the union of these sets. And then because they are mutually exclusive, we can separate PA into PA4, PA5, and PA6, and then we sum up of them. From the previous result, PA4 is equal to this, and PA5 is equal to this, and PA6 is equal to this. And then we get the probability of A is 15/21. Okay. Okay. Could you repeat the idea of this this problem? Great. Let's move to next slide. Yeah. In this slide, we consider non-balanced eight-sided, and yeah, similar with the previous example, the probability of number E is I times T. We must find the value of T. Yeah. Okay. Yeah. Maybe we will move to the next slide. And if we have spare time in this meeting, we move back to this exercise. Okay. And for the next session, we will deal with the counting techniques. This is useful for us to count the sample space where it is big. We can use this theory to count outcomes in a large sample space. For the first principle, that is multiplication principle, that said if there are m ways to do one thing and n ways to do another thing, then there are m times n ways to do both of things. Just multiply m and n. And after we multiply these two values, we can get how many ways of doing both things. An example, in a dealer, you can they offer a car with 3 model of door: convertible, 2-door, and 4-door. And then for the rear wheel, covers all solid. And then from this combination, how many different products can be offered to the customer? Because the value is quite small, that is the model and wheel. We can consider model as the first thing and the wheel as the second thing. In this case, model has three types and the wheel has 2 types. And then we can get 6 different models or 6 different arrangements. 1, 2, 3, 4, 5, and 6. And because this number is quite small, we can list all of them in a picture. Now, just multiply all ways of things. Yeah, and for this problem, how many different outfits can be advertised? Who can answer this question?
20, sir.
20, yes. Yes, right, Owen, because the first thing is choosing the type of the color of sweater, and there are 5. And then for the slacks, there are 4. So from the multiplication principle, we can get 20 different outfits. Then if the previous slide we discussed about 2 things, we can generalize the multiplication principle into 3, 4, and so on. So if we have m1 ways to do first thing, and then m2 ways to doing second thing, and m3 ways to doing third thing, we can get m1 times m2 times m3 ways to doing these things. As an example, if Pioneer manufactures 3 models of receiver, and then 2 cassette decks and 4 speakers, and then they combine them into a system and solve it in terms of system, then from the multiplication principle, we can, how many different systems?
24, sir.
24, right? Yeah, we can consider the stereo as the first thing, the cassette decks as second things, and also speakers as the third. Yeah, and then just multiply 3, 4, and 2. Okay, Okay, thank you for your answer. Yeah. Yeah, I hope you can understand this usage of multiplication principle. And then for the next, yeah, the question before this slide deal with two sources. How about this exercise or this problem? We just only have some resources, that is the economic students in FAB. How many different ways the MESPA can choose its president and vice president? This is the symbol of president, and this is the for VP or vice president. We take them from the economic students. How many?
9,900, sir.
9,900. Why can you have that the value from what?
Because for the first, for example, for the president, there's 100 choices. There's 100 choices.
Yeah.
And when you already choose the president, there are only left 99 people. So yeah, 100 times 99.
Right. Thank you. For the first thing, for the president, we can select from these 100 students, and then because one man or one student cannot hold these two positions, yeah, of course, for the vice president, we only have 99 people, so we can multiply it and get this result. Okay, thank you very much. Yeah, great. And then we move to the next principle. We combine the sampling with replacement, and we consider is the order important or not. For the first case, that is resampling with replacement and the objects are ordered, or we consider the order of this selection. It's this formula said that if random samples with size k is taken from n objects, and then we assume that with replacement and the order is important, then there are n to the power of k possible ways of selecting k tuples. Yeah, we must consider that it is with replacement, and we care about the order of the outcome. For the first example, that is a die which is rolled 4 times. 4 times means it is associated with no replacement, since we can get this result 1 1 2 2. Yeah. If the first rolling is shows 1, and obviously the second one can be also contains 1, right? So we consider it with the replacement, or we can repeat the previous result to the next result. And then for this die, it is clear that the value of n is 6, because we have only 6 outcomes, and then because we roll it 4 times, the value of k is 4. So by this theorem or this result, there are 6 power 4 tuples of the way or the way of selecting. And then for the next example, that is we have a box contains 8 balls, and then we randomly select with replacement 6. Analyze first. The n objects given is 8, and the value of k is 6. So the sample space will consist of 8 to the power of 6 tuples. This is for the sampling with replacement, and with the objects are ordered. The order is important here. Next, for the second case, that is sampling without replacement, and the objects are ordered. Before we talk about the formula, we consider the factorial notation, that is n factorial, and with this sign is equal to n times n minus 1 times n minus 2 until times 2 times 1. And then if r objects are chosen from a set of n distinct objects without displacement, the ordered arrangement is called a permutation. This is just a term about r objects which is chosen from n objects without replacement, and yeah, we said the order is the permutation. And how many permutation we have? It is answered from this theorem. That is, the number of permutation of m objects which is selected from n objects is this n permutation m. That is n factorial divided by n minus m factorial. And you can simplify it to this term. Let we see about the examples. For the first examples, we must find the number of permutation of 3 letters from 4 letters A, B, C, and D. That is, we must arrange 3 letters. Because it is assumed that there are no repetition about the letters, we can use permutation here. And yeah, of course, we consider about the order of the letters. So we're using permutation. The number of permutation is 4 permutation 3. That is 4 factorial divided by 1 factorial. 4 factorial is equal to 4 times 3 times 2 times 1 divided by 1 factorial, of course 1. And this is 24. So we have 24 arrangement of 3 letters, which is taken from 4 letters A, B, C, and D. Yeah, by the permutation formula, it will be easier to find the number of arrangements, right? Rather than we list all of them by hand. Yeah, it is not efficient. Okay, this is for the second case. And then we go to the third case, that is sampling without replacement and the object are not ordered. Are not ordered means we don't care about the order. It is different with the permutation because in this case the orders of arrangement is not important, and the arrangement is called combination. How to count the amount of combination? We use this formula, that is the number of ways in which m objects can be selected, of course without replacement, from a collection of n distinct objects is this n combination n, that is n factorial divided by n factorial times, I have a mistake here, it should be n minus m factorial. I'm sorry. And we can simplify the formula to this form. And a remark, of course, because we don't since we do not do replacement, so the value of m is from 1 until n. Yeah, it not make sense that if the case is without replacement, we select, for example, we select 10 objects from 9 objects. Yeah, it is not possible, right? Because we have only nine objects. We do not replace it. Then we cannot select 10. Yeah, for the example, it is quite different with the selection of president and vice president. That is, from 40 staff in HIMIASPA, we will send a delegation for Osmina, which contains only 10 members. And yeah, how many ways to select the delegation? How many? Let's consider first. Is it the order important or not? So illustration, we from HIMIASPA, there are 40 students, and then we must select a group of 10 people. And yeah, assume that there are no structural in this set. That is no president. There's no the president or the secretary also. And just an delegation. Yeah, yeah. Of course, from this problem, we can get that we don't care about the arrangement. Just pick 10 people from 40 staff. So we deal with the combination. And yeah, the whole resources consists of 40 students, and then we select 10 of them. So the ways is the combination of 40 and 10. That is 40 factorial divided by 10 factorial times 30 factorial. It is quite a big amount, so you can use the calculator to find this value. And yeah, these are example for your exercise, and we move to the last case, that is sampling with replacement and the object are not ordered. Yeah, in my point of view, this case is a little bit quite hard to produce the formula. So we must imagine what happened in this case. In this case, we do a replacement after we take a thing, right? As an example, if we have a box of balls, and then we want to create a sample which contains three balls. We will pick 3 balls and do replacement. So yeah, of course, because we want to select 3 of them, and there is a replacement. Of course, because our sample size is 3, we do replacement 2 times, right? So actually, the whole object consists of 6 elements, and then we pick 3 of them without caring about the order. So in this case, it is equivalent with the combination of this. Note that 2 is 3 times 1. So in general, if we want to create a sample with size k, we do k minus 1 replacement. So the total of object is n plus k minus 1. K minus 1 represent the amount of replacement. And then since we don't care about the order, we use combination and select k of them. Yeah, this is the outline of our formula. Okay, after these 4 cases, is there any question for me, please? Great. I hope you can receive the idea of these 4 cases. And yeah, it is on the example, if we have 15 balls and 4 balls are selected with replacement and without care about the order, we can use the previous formula, and the number of possible samples is this. Yeah. Yeah. Okay. And then this is the last slide for our discussion in counting techniques. You can use this exercise for yourself, and or you make a group to discuss it. It's up to you. Okay. We have just finished the second part, and we go to the third part. That is the conditional probability. In this kind of probability, we will deal with 2 events, E and F, and then we ask the conditional probability of E given that F. So it's clear that F is happen, and we ask what is the probability of E. And the probability denoted by this notation, and it is defined as the probability of E intersection F divided by the probability of F. And for this formula, we must consider that the value of PF is not 0 or it is greater than 0. One remark for this definition, it is important in a problem to determine what is the given the given event and the event that asked in the question. Yeah, for the first example, let me see in the experiment of tossing two balanced dice, and we have two events. A event that the sum of the first is 9, and B be the event that the first the first value of the first die is equal to 4. And then we must calculate this probability definition. P A given that B. Yeah, from the previous definition, this value is equal to the probability of A intersection B divided to PP. Okay. Okay. I will give you a couple of minutes to think about the answer. Please, you can do it by yourself. And once you have one of you get the answer, please please share to us. Yeah. The first step, you can list all of the members of these events. It is the first step. Okay. Are you finished for this question? And who want to be a volunteer to share his or her work?
Is it 1/6, sir?
1/6. Yeah, the final answer is 2. And could you share to us why we can use why we can get that answer? What are you doing with these steps, Kenda?
Okay, the first one, the A is 3, 6, 6, 3, 4, 5, and 5, 4.
Yes, like this.
Yes, the same. And the B one is 4, 1, 4, 2 until 4, 6.
Or six.
And the P, A, and B is only the 4, 5.
4, 5, right. The
Yeah, so it
yes,
is 1 over 36 divided by 6 over 36.
yes, like this. And you get the final answer is 1 over 6. Okay, great. Thank you, Vendra, for your answer and sharing. Is there any question from the other students? No. Great. Yeah. Let we move to the next question. And in this question, I don't mention what is the event A and B. You must define it by yourself. This you can use your time to find the answer. Please. Yeah. Okay. Is there anyone who finished this problem?
Is it also 1/6, sir?
1/6, right? And Sally, can you share to us what is the procedure?
Okay, so we have two sets. Let's say there are set A and set B. Set A includes an event where the John card is 10. So inside set set A, it's only 10.
And it only 10.
Set B is an event where the John card is at least 5. So there is 5, 6, 7, 8, 9, 10. And then we have an intersection between set A and set B, which is 10.
Only 10.
Yes, and then we compute using the formula. So there is 1 over 36 divided by 6 over 36.
Yeah. And the question is the given is A, right? And yeah. Given that at least 5. Sorry. The probability like it, Sally, A given that B.
Yes.
Yes. Yeah. Thank you. And then this probability is 1 over 10, and this probability is 1 over 6. Yeah. So it produced same result as the previous example, that is 1 over 6. Yeah. Thank you, Sally, for your sharing to us. Okay. Yeah. Yeah. In conclusion, it is important to define the event first, and we must use the right situation or the right notation. It is different if we talk about the probability of F given that E. It can be different. So we must be careful about this statement. Okay, good. Is there any question from you about these two examples? Okay, no. Okay, good. Yeah, this is the next exercise for you, and yeah, let me go to the next slide. Okay, like the definition of probability by axiomatic, the conditional probability also has several properties, which is listed in this box. Yeah, if you see the the first one is yeah, similar with the previous property set, and after that for number 4 we can see we can compute the probability of intersection A1 until AN with this formula. Yeah, it comes from the definition of probability from the conditional probability. That is, it is equivalent with this. So yeah, this is equivalent with this, and yeah, we can generalize it to the case of n elements or n events. I'm sorry. Yeah, for the illustration, we will discuss an example about the fourth properties. That is in this example. Yeah. In a basket, there are 25 apples and orange. 20 of them are apples. And then we randomly pick in sequence without replacement 2 fruits. We want to determine the probability that both of them are apples. So what is the events of this problem? And yeah, we for the hint we will use the properties number 4. But firstly find the events. Yeah, that discussed. Or is there any answer from you? Okay, if there is no, we will discuss it together. Firstly, we define A to be event, that is the first fruit is apple. And similarly, we define B as the second fruit is an apple. Because our event is both of them are apples, it is similar to find the probability of A intersection B. That is the event that both fruits are apples. And then from the fourth properties, we can see that this probability is equal to PA times this probability. Okay, let me see why PA is 20 probability divided by 25. In the box, there are 20 apples and 5 oranges. Because we do it without replacement, then pick a fruit and don't replace it. So when we are in the first event A, the whole fruits are 25 and apples, and there are 20 apples. So the probability of choosing apples is 20 divided by 25. Okay, and then for the conditional probability of B given that A, that is A happened, that is our first fruit is apple. So for the second fruit, the let's say it is an apple. We don't replace it, so the basket is consists of 24 fruits now, where 19 of them are apples and 5 of them are oranges. So for this conditional probability, we have the probability is 19 divided by 24, like this, and then we combine it, and we find and we get the probability is this. Okay, could you receive the explanation of this problem? Yeah, I hope you can receive the idea, and yeah, and the illustration is play important thing in this problem. Okay, good. If there is no question, we move to the next question. Yeah, I only generalized the previous example, the previous problem with another cases, and for this exercise, we randomly pick without displacement 3 balls, and then yeah, similar with the previous example, the question is the probability that 3 balls are white, and then you can also replace the term white with blue and green to have another question. Okay, yeah, I left it as an exercise for you. And now we move to the next concept, that is two events that are independent. In this case, we have two events A and B with their probability isn't 0. They are said to be independent if this equation or this equation are whole. If they are not independent, we said that they are dependent. And then for the another perspective of the definition, we call that from the definition of conditional probability, we have this equivalence, and if A and B independent, so we can replace this with PA and then get this formula. So it is an alternative to determine whether A and B independent or they are dependent. And for the example that we recall our previous example, that is deal with two dice, A1 and A2, like this. If we see that their intersection is consists of an element 4.44,2, and then the probability of this event is 1/36, and the probability of E1 is 5/36, and the probability of E2 is 6/36. And with the second definition, we can check that they are different. So because they are different, because they are different, they are dependent. These two events are dependent, since these two values are not equal. Okay. Yeah, this is the end of our discussion about the conditional probability. And next, we will deal with the bias formula. Recall from the previous discussion, this formula is equal to this equation, and then note that A can be written as the union of these two sets. You can use the Venn diagram to illustrate it, and then we also have they are mutually exclusive. So by our probability axiom, PA can be written as these two summation, and then this term is break down into this multiplication, and similar with this, and yeah, because we have the properties that PB complement is equal to this, we have this equation, and as a result, we can replace the PA with this right hand side. So we have this formula as a conclusion, and if we see this formula help us to count the probability of B given that A in terms of the probability of B, the probability of A given that B, and the probability of A given that B complement. It is very useful to find these values. And next we will see this application, the application of this formula to this example, right? In this example, we have two urns, A and B, where A contains two white marbles and 10 and 7 black marbles. This is for the urn A, and for the second urn, we have 5 white and 6 black. And then to decide where we take the marbles, we flip a coin, a 5 coin. So that take the marble from the urn A or B, depending on the outcome of that coin. And then the question is, what is the conditional probability that the outcome was heads, given that a white marble was selected? Okay. For the term of the event, we can see that the first thing is the outcome was head, and the second one is a white marble was selected. So that we must decide, we must define the events, because we have only these two statements. We can define the events as this. Let W will be the element, will be the event that a white marble is taken, and it's be the event that the coin comes up. Because there are no rules in this problem, we can define that, we can assume that if head comes up, then we take from A, and clearly if the result is tail, we take from B. After that, by the question, the given condition is the white marble. So our problem is computing the probability of H given that W. Yeah. From the information of our problem, we cannot directly we can't directly compute this value, because yeah, we only know that if the coin shows head, we go to the urn A, and then otherwise if it comes up tail, we go to the second box, second urn. By the bias rule, we can compute this by this formula. Let me find the value of PW given that H. That is, we know that H comes up head, and then what is the probability of white? Yeah, I mean in this problem, T is equal to H complement, because there are only two outcomes, and either it is H or H or T, I mean. So H complement is equal to T. Yeah. Can anyone give the answer of this probability? What is the probability of white if we know that H is come up?
Is it 2/9, sir?
2/9, right, Stella? Yeah, thank you. Because we know that H head, we go to the urn A, and then just find the probability of W, that is 2/9. And okay, thank you. And Sarah, can you continue it?
The probability of H is half.
Half, yeah. Is it equal to PT or PH complement?
Yes, I think it's
yes,
equal.
yeah, because the coin is square. And then the last,
so it's basically P W given by T, so 5/11.
5/11, right? Because if T shows up, we go to the urn B. So just count from the urn B. What is the probability of white is 5 divided by 11. Thank you, Stella. And yeah, after that, just substitute all of this P to this result. and you can get the result. Okay. And before we go to the next example, is there any question for this problem? Yeah, it is an interesting problem, and we see the usefulness of the bias, the bias formula. Yeah, and for additional exercises, you can use these two questions to discuss with your friend. Okay. If we see the previous formula is consists of two events, right? Two events, that is B and B. Consists of A and B. How if we deal with the generalized form, that is we have n and events like that. Yeah, to answer to produce a new formula, we use the law of total probability, and before we discuss it, we give the definition of the partition. If we have set S, the collection A1 until AN is called the partition of S if, number one, S is equal to the union of all of them. And then for every two sets I and AJ, for different I and G, they must be disjoint. So if I illustrated the partition, it's like this. It is S, and then we divide S into three parts, S1, S2, and S3. It is clear that if we add all of them, it produces S. So the first rule is obtained, and for every two different parts, it is there are these two, right, like this. And then the law of total probability said that if we have a partition of S where the probability of AI is greater than 0, then for every event B, we can write PB as this equation. And of course, this equation is a generalization of the equation in our material in bias law. It's just generalization. We talk about n partition, n sets that partitioning S. And for the next, what is the impact of the previous formula? It's given by this result. That is, if S is a partition, if A1 until AN is a partition, for every event B, we can get this formula. The probability of AJ given that B is equal to this. Yeah, this summation is actually the PB. So for our general problem, it's important to define the partition first. After that, we apply this formula. Yeah, just an application. So yeah, the first thing is to produce a partition. Let me apply our previous result to this example. In a class, there contains 70% male and 30% female, and it's known that 5% of males and 10% of females got A. And then we select a student randomly, and we know that his or her score is A, and we and problem is, what is the probability that this student is a male? Yeah, this is the problem. Okay. Yeah. You can do it for several minutes. Okay, who have finished this example? Okay. Okay, that I write down the information in our class. There are 70% male and 30% female. 5% got A and 10% got A. There's a student randomly selected and get A, and we must find the probability of that it is he is a male student. Anyone can give the at least the partition. What is the partition of this element, this problem? Okay. Yeah. Okay, if there's an idea, let we discuss it together. Of course, the set of male students and female students form a partition, right? Because all of the class is consists of these two groups, and these groups are disjoint, right? So M and F are the partition of this M and F are partition. So let M be the event male student is selected, and let F be the event that female student is selected, and A event that student got gets A. And then our task is to find the probability of M, because we ask for what is the probability that this student is male. So it is probability of M given that A. And then we apply our formula. So the probability of M given that A is equal to Pm times P A given that M divided by Pm P A given that M plus Pf times P A given that M. Okay. Okay, let's find all of these values. For the first one, what is the value of PM? Probability of a male student is selected. PM is equal to
70%.
70% or 0.7. Please continue it, Owen. What is
And then the probability A given M is 5%.
5% because we given that the student is male, and what is the probability? He got A, right? It is 0.05, and then
PM and BAM is the same.
Same, right? Plus,
and then the probability of female is 30%, and then the
30%.
probability of A given female is 10%. Yeah.
10%. Right. Thank you, Owen. And yeah, you can continue to compute it by yourself. Okay. That's all of this example. Is there any question? Thank you, Owen. Okay, that's the question. Yeah, it is important to define what is the event, and then what is our task or goal, and then yeah, use the previous formula. Yeah, as I mentioned before, that is steps to apply Bayes' rule. Yeah, create a partition is the first step to do this, and then you can use the formula to find the desired probability. And then for our closing, we deal with three anti-missile defense system. And then from the design, each of this has an equally likely chance to detect and destroy a missile. However, if we test it in the field, we can get that the first system will usually attack 10 of 12, the second is 9 of 12, and the third 8 of 12. And then we have observed that the target has been detected, and then we will find the probability that the third anti-missile system is used. Okay, because there are three systems, we can write the partition as S1, S2, and S3. They produce a partition for this problem. And then we define these events. That is, S1 is event that the first anti-missile is used, S2 second, and S3 for the third. And D means the event that the target is detected. And from our question, we must find the value of P. The value of P as 3 given that P. Of course, once again, apply our previous formula. It is equal to this expression, and then we can find all of them. For the first one, the probability of D given that S1 Means we consider the first anti-missile system and find the probability of destroying the target. So from the data, we get that the probability is 10/12. It is this, and similarly for the second and third anti-missile system, that is 9/12 and 8/12. And for the final one, the probability of SI is equal to 1/3, because they have equally likely possible to destroy. Yeah, so after that, you can substitute, you can put into this formula and count what is the final answer about this this probability. Yeah, and yeah, in conclusion, the definition of the creation of the partition is an important thing in this problem. Okay, and for the final one, yeah, these are two exercises for you, and yeah, you can discuss it with your group. Okay, yeah, I think that's all of our meeting today. Before I close, is there any question from you? Okay. Okay, no. Have you filled the in Google form in the chat box? Oh yeah, yes. Thank you. Yeah. Before I close this session, before we